All right. Hello. Sorry about the technical difficulties. Welcome to day 2 of game theory. Um, Today we are going to be discussing sequential games, which you may remember, hopefully do remember, from yesterday's class. We discussed several kinds of games, and one of the categories we discussed were sequential games. So, what is a sequential game? A sequential game involves players choosing options one after the other. That's the definition of a sequential game. We had a slightly more nuanced definition last time, but some examples are chess, checkers, Go, basically any board game. Just to make sure people understand the concept and or remember it from last time, can we just get a couple of examples of some sequential games? Yeah, Go Fish, Uno. Yeah. Poker, Monopoly. Yeah, people are getting it. All right, just making sure. Okay, so how do we represent the sequential game? So we need a way to mathematically represent the game in such a way that we can understand each player's thought process and how each player should act. So we use what is called a game tree in order to demonstrate this. So each point on the graph, each node, represents a decision that is being made. That's called a decision node. Um, and we'll explain what each decision node acts like, I guess. So how do you read this? What does this mean? So basically, you read it from left to right or from top to bottom sometimes, depends on how the game tree looks. But in general, it's left to right. But as you can see here, Anne has to make her first decision. She's either going to choose option A or option B, right? These are her two decisions at this point in the sequential game. Now, based on her decision, Bob must react. So if Bob chose option C or D, it will end up with a different payoff. And Bob can go this way if Anne previously chose A, and Bob can go with either of these if Anne chose option B. So we can see that at the end of the game tree, there are some numbers. So these numbers are the payoff numbers. If you recall, the payoff is the numerical value assigned to how much each person wants a specific outcome, which is a fancy word of saying a bigger number for you is better. But in this case, Bob can either choose option C or D, right? And here, if he chooses option C, he'll get 9. So these two numbers separated by a comma, the first number refers to the first person, and the second number refers to the second person. That's just how it works. Sometimes it'll be clear, like if they use color coding, but in general, the order of these numbers in the payoff is relates to the order of when decisions are made. So because Anne makes the first decision, her payoff is first, and because Bob makes the second decision, his payoff is second, right? So does everybody understand that? Because we're going to get into how to understand, I guess, solve it. Okay, I'm seeing thumbs up and a yes. So how do we detect what outcome will occur? So we can we can discover what the final outcome will be using something called rollback equilibrium. That is what the final outcome is called, the optimal outcome. And what we're going to use is a technique called backwards induction. One of the key principles of this is that we know that every player is rational. So each player is going to necessarily choose the outcome which grants them the highest payoff. So let's look at our next example again. So let's look at both our previous example. We have to start at the end and then work our way up to the beginning. So in this case, if Bob chooses C, he'll get a payoff of 9. And if Bob chooses D, he'll get a payoff of 5. In the other case, if Bob chooses C, he'll get a payoff of 4. And if Bob chooses D, he'll get a payoff of 6. So in the first case, if Anne chooses A, which one will Bob choose? Will he choose C or will he choose D? Yeah. And in the second case, if Anne chooses B, will he choose C or D? Exactly, yeah. So we know this. So Bob is going to choose 9 or 6. If Anne previously chose A, then Bob is going to go with 9. And if Anne previously chose B, he's going to get 6. So now let's go back to Anne, right? So we know Anne knows that depending on what decision she makes, Bob's decision is basically already decided, right? So she understands that if she chooses A, then Bob is going to choose C. And if she chooses B, then Bob is going to choose D. So based on this, she can rule out the outcomes of her choosing A and Bob choosing D, and as well as the option that she chooses B and Bob chooses C. Because all players are rational and all players understand that the other players are rational, Anne knows that Bob won't go with those options. So she only has to look at, she chooses A, Bob chooses C, and she chooses B, Bob chooses D. So which one will she go for, knowing this? Yeah, she'll go with option B because in that case, she gets a payoff of 8. Exactly. So that's how you read a game tree. This is a very simple one. So let's look at some more difficult ones. So she'll choose B, Bob chooses D, and the final outcome is Anne gets 8, Bob gets 6. So how can we make this game more complicated? So first of all, we can include nature. Sometimes choices aren't up to players, but sometimes nature, which is just a fancy way of saying probability, right? Sometimes you do not control what will happen. You can't control the weather, and the weather isn't really a player. That's up to chance. Another way we can do it is by adding more players. That just means that more players are going to want their outcomes chosen. It sounds more complicated, but it doesn't actually make things that much more difficult. So here's a huge game tree I made at some point. Is air different from nature? Because we assume that, I mean, what do you mean by error, I guess? Because players don't make errors because they're rational. And we assume that they can make the correct thing all the time. So an example of,
Can I talk?
yes, go ahead.
So what I actually don't know if this is the right term, but by error I meant like say Anne chose option B, but for like there's like a 5% chance that whatever she chose, like the opposite happens. Something is that I know there's a word for it, but it's not coming to me. Or maybe I'm just chatting shit. I don't know.
No, I understand what you're saying. That is nature. Simply put, because there's a probability of something else happening, that is nature. But the way we would put that in the game tree is instead of this very easy linear game tree, what would happen is that Anne would choose option B, and then another node would occur in which nature makes its decision. So let's look at this chart. As you can see, nature makes the decision whether to do this or that with certain probability. So that's what happens. I don't know. Okay, yeah. So let's examine this game tree. So we have 3 players now, Anne, Bob, and Carl. Yeah, recording. We have Anne, Bob, and Carl. ABC, very convenient. And Anne likes to read, Bob likes board games, and Carl prefers movies. So when we look at this, and we're trying to decipher what are they going to do that day. So Anne can initially either choose to read by herself, go to the movies with friends, or play board games just with Bob. If she reads at home, that's that. If she chooses board games, then Bob gets to choose which board game they play. But if they go to the movies, then Bob can decide whether they are going to invite Carl or not invite Carl. If they don't invite Carl, then they just watch a standard movie. But if they try to invite Carl, they have to email him. but they're using a really bad email service. I'm trying to think of bad email services, but the only one I can think of is Apple. Don't use Apple email, it sucks. So there's a 25% chance that it glitches out and Carl does not get the email. However, if he does get the email with 75% chance, then Carl gets to choose the movie. Carl can basically watch any movie anytime, so he will get a very little difference in payoff from watching a bad movie versus watching a good movie. So how do we think we have to do this? Where should we start? It's a bit long, so I'll give you guys a quick second. You guys shouldn't solve it right now because I'm going to do that, but just where should we begin looking, I guess, is a good way of putting it. Yeah, exactly. We're going to have to start with Carl. Yeah. So Carl can either choose to watch the good movie or watch the bad movie, right? So let's compare his payoffs. Remember, we go in the order of the people is the order of the payoffs listed in commas. So Carl, if they watch the good movie, has a payoff of 7. If Carl decides to watch the bad movie, then he has a payoff of 6. So Carl is going to choose to watch the good movie, obviously, because he doesn't want to watch a bad movie. So now let's move to Bob, right? So let's start off with the nature. So Bob can either choose to invite Carl or watch without Carl. So which one will he do? This one's a bit tricky. So we know the payoff for watching without Carl, right? It's 4. But how do we describe the payoff of what happens when they do invite Carl? So because there's probability, how should we represent that? How should we represent that payoff, I guess? Hypothetical payoff. How do I put that? Okay, I think you guys are getting it, at least. Yeah. So basically, we know that because there's a 75% chance that the email will get sent, we can multiply the probability that it does get sent with the final payoff that occurs when it gets sent. And then we add to that the probability that the invitation does not get sent with the final outcome when it doesn't get sent. So what we are going to do for the payoff, if he invites Carl, is I have a calculator here. So basically what we do, so with 1/4 chance, 0.25%, 25% chance, Carl will not get the invitation. So the payoff there for Bob will be 3, right? And then to that we add 75%, 0.75, times the payoff of when Carl does get invited, which is in this case, because when Carl gets invited, he chooses to watch the good movie, 5. So it's 1/4 times 3 times 3/4, that 1/4 times 3 plus 3/4 times 5. So okay, I did something wrong, but give me a second. 3/4 plus basically you get, so if Bob decides to invite Carl, then he will get a payoff of 4.5, including this probability with nature. But if he chooses to watch without Carl, then he only has a payoff of 4. So even though in some case Bob will actually get a lower payoff than he would if he chose to watch without Carl, because of the probability and the likelihood that Carl's probably going to get the email, Bob is still going to choose nature because it's the higher payoff using probability. So now let's look at the other case where Bob controls, which is playing board games. So Bob can either choose to play Monopoly, Risk, or Clue. So which one is Bob going to choose? Let's make sure that we all understand what's going on. Okay, yeah, Monopoly. Exactly. Because if we look at it, if he chooses Monopoly, he gets a payoff of 3. If he chooses Risk, he gets a payoff of 1. And if he chooses Clue, then he gets a payoff of 2. So in this case, Bob is going to want to choose Monopoly. So now Anne has to analyze all of this, right? So she can either choose to read at home and get a payoff of 2. She can choose to play board games with Bob and get a payoff of 1. Or she can go to the movies with Bob and get a payoff of 4.5 again. I'm very glad I made those numbers the same. Because of nature, we know that if she chooses to go to the movies, Bob's going to invite Carl, and she will and so Anne with 25% chance will get 3, and with 75% chance will get 5. So that payoff is 4.5. So if she reads at home, she gets a payoff of 2. If she goes to the movies, she gets a payoff of 4.5 uh, with probability. And if she plays board games with Bob, she gets an outcome of 1. So which one is she going to choose? Exactly. She's going to choose to go to the movies. And thus, uh, the two possible outcomes are just the best outcome, 557, when they choose to all go to the movies and Carl comes and they watch a good film, or because of the nature and the probability, it's going to occur. Anne and Bob will go, but Carl will not be present. So yeah. So what are some real world applications of sequential games? The most obvious one is that chessbots use a very limited rollback equilibrium in order to see the future and determine plans of action. The reason they can't do complete rollback equilibrium is because when you are doing a sequential game, you have to map out all of the possibilities, right? But even in the first move of chess, you can move any of the pawns or the knights, right? There are I so each knight has 2 different places it can go. Each pawn can either has 2 places it can go. So there are like 20 different outcomes, even based on only the first move. So they can't do it completely, right? Even though it's a computer and it can handle a lot more data like that, there is still a lot of things that it needs to think about. Yeah, exactly. The game tree would just explode, right? So what are some other are we going to go over stuff like alpha beta pruning? No, we aren't. So what are some other real world applications you can think of? Like, playing games that have a point system. Yeah, exactly. Basically, if you're trying to keep track of what possible things are going to occur, so long as you can make a decision tree, as long as the options are discrete and easily definable, then yeah, you can create a bot that will look at all the possibilities and create just a game tree and try to get the best outcome. Exactly. What are some other examples? To be honest, I haven't thought about all these examples. Using a game tree to play tic tac toe is, I think that's a bit much for playing tic tac toe yeah, as an English project. Okay. Um, I mean, yes, using a game tree is what you should be using to do tic tac toe, but I feel like it's a bit much. It's so funny. Okay. So let's do a little bit more practice. So I'm going to let you guys do it. And then, so you guys take your time and then give me your answers, I guess. So in this case, there's 2 companies, and organization B is already in some market, and organization A is deciding whether to enter said market. So based on this game tree, should organization A join the market, and what should organization B do if they do join the market? So I'll give you guys until somebody gives me an answer to this, I guess. Uh, so if you want to, I mean, if you guys take too long, then I will stop you. But okay, yeah, that was fast. Yeah, that's good. It's good when you guys are fast. So organization A is going to choose to enter the market, and organization B is going to choose to accommodate them. So let's quickly do this a little bit more formally. So organization B, given the fact that organization A entered, is going to choose to accommodate, because if they choose to fight, they get a payoff of -3, which is bad. And if they choose to accommodate, they'll get a payoff of 1, which isn't great, but is certainly better. So based on that, organization A, if they choose to enter, they will get a payoff of 1, as organization B is going to choose to accommodate. And if they do not enter, they get a payoff of 0. So they're going to choose to enter as opposed to not enter. Exactly. Yeah, you guys are good. And that's good. Okay. Next one. So we have players 1 and 2. And this demonstrates that people can take turns. This is some random board game where players take turns, for example. And at each time, each player can either choose left or right. And whenever a player chooses left, the game ends with a specific payoff. So which one are people going to choose? This one might take a little bit more. So once again, I'm going to let people do it. And then when people have done it, I'll give the answer. So I guess just phrase it in the form like left, right, left, or right, right. Well, you can't do that. Okay. Let me check. I forgot to check this question ahead of time. So let's start off at the very end of the tree. So player 1 is going to either choose left or right, right? So if they choose left, they get a payoff of 3. And if they choose right, they're going to get a payoff of 2. So now let's go up the tree. Player 2, if they choose right, they'll get a payoff of 1, because then player 1 is going to choose left. And if they choose left, then they get a payoff of 2. So they are going to choose to go left. Now, if player 1 is again making the decision, they know that if they choose right, then player 2 is going to choose left, and then they'll net 0. But if they go left, they net 1. So in this case, player 1 is going to choose left, and the game immediately ends. So a lot of people in the beginning went with right, right, left. I'm trying to figure out why. So what is confusing people, I guess. If it was something as simple as getting confused by players because this game tree doesn't look particularly good, that's fine. But if there's a real issue, I mean, that should be resolved, I guess. So trying to figure out why you would choose right, right, left. Hmm. Yeah, I mean, the correct answer is player 1 immediately goes left, but earlier on, people were saying right, right, left, and I'm trying to figure out why. Oh, okay. So once again, we have to remember what payoff reflects what person. Because player 1 made the first choice, then their payoff is represented by the first number. And because player 2 made the second choice, their number is represented by the second number. So if player 1 goes left immediately, they get a payoff of 1, and then player 2 will get a payoff of 10. So was that the issue? Oh, okay. Okay, yeah. So if it is, yeah, it wasn't just one person, I guess is best way to put it. Player 1 and player 2 are separate people. This isn't the greatest looking one, but I thought it was good. Sometimes people get confused about payoffs, and instead of trying to, and some people think that you're trying to win, get more points than the other person. And sometimes you have to kind of teach them that they don't care about the other person. So that's why I chose this, even though it's not great. So this is how you solve a very simple sequential game. But if you want to do harder ones, sometimes a game tree isn't the best option because there are many outcomes. Or maybe the outcomes aren't even discrete. So let's look at a pretty interesting question. I think it's probably the most interesting question that uses sequential games early on. There are other examples of interesting games that I might get into if we finish early. So the pirate game, this is very fun and very cool. So 5 pirates have 100 gold to split amongst themselves. They've chosen an interesting way of splitting the pot. So the first pirate gives a proposal for how many pieces of gold each pirate will receive. Then everybody votes yes or no on this proposal, including the proposer. If 50% or more of the pirates approve the proposal, then it is accepted and the game is done. The gold is split and everybody gets a payoff equivalent to how many gold coins they got. Otherwise, if they decline this, pirate 1 is killed and pirate 2 proposes a new way of splitting the gold. And now the remaining pirates vote on the new proposal. Once again, they vote and pirate 2 is killed if the vote fails. And now pirate 3 proposes a solution. And this will continue until some vote passes. So in case of a tiebreaker, okay, very funny person who happens to know the answer, spoiling it. Tiebreakers are decided by the proposing pirate, and pirates would rather kill than they would settle. So, ignoring the guy who knows the answer, what do you guys think you would do? I taught this class some time ago, I think exactly 1 year ago, and there was not person didn't get this question, but there was a question later on that somebody answered when I was giving it. So I'm used to people answering my questions before I'm finished. So just off the top of your head, what do you think would be best course of action? Yeah, this is a pretty common riddle, so I can understand why you would know it. It's not like some magically hidden thing that I conjured out of my mind. Okay. So people seem to be getting the correct answer, but I'll explain it for people who don't know how to do it. 9811, yeah. Okay. So let's examine the question in greater detail. So here are 5 pirates. We are going to sort them by chronological order of when they appeared in various media. So this is their age ranking. How many pirates do you know? I don't care. I just chose some random pirates that I happen to know of, even though technically one of them is a fake. But so much like backwards induction, we are going to start looking at this question from the end. With most sequential games, that's what you want to do. You want to look at the very smallest case and work your way up to larger cases. So if there's only one pirate, then he is going to choose to keep all the gold to himself. It's that simple. And because there's only one person voting, he votes yes, and he gets to keep all of the money. So now let's consider what occurs when there's 2 pirates, where what do you think the proposer is going to try to do? Remember that the proposer, because they're the eldest pirate, gets to break ties. Yeah, exactly. The proposer is going to say, I'm going to keep all of the money and you get none of it. So because the tie break is broken by the voter, the current eldest pirate gets to keep all of the money for himself. So the first pirate gets the maximum payoff and the second pirate is sad. I have way too many. Okay, there's a nice filler slide. Okay, now here's the third pirate scenario. So what do you think the third pirate is going to do? Okay, yeah. So let's so he's going to split it 9901. So the reason behind this is that the first pirate is remembering what happens if he denies the proposal. If he says that he doesn't want it, then he will get nothing, right? So he knows that if he votes no on this, he's going to get no coins. So even one coin in this case is a rather good thing. So the voting, the king pirate is going to say yes. The second pirate is going to say no, but the last pirate is going to say yes, even though he only gets one coin. So the split is going to be as so. Okay, now we have four pirates and bad cropping. How do people think this one's going to go? It's similar concept, but now we have to extrapolate a little bit. Okay, so people seem to be getting it. Yeah. So the current for a king pirate or eldest pirate, I don't remember what your word I'm using, is going to split the coins as so. He's going to give no coins to pirates 2 and 4, but he's going to give it to pirate 1. So I mean pirate 3, pardon. So pirate 3 is remembering that if this current pirate gets killed, then he's going to be stuck in a situation where he gets no coins because the third pirate is going to suck up to the fourth pirate. It's so very hard to talk. So the voting is as shown, and the tiebreaker is broken by the eldest pirate. So the distribution is like this. So now all 5 pirates are present. This is our base scenario. So what happens here? Yeah, so people are getting it right and understanding the concept. So Pirate 5 is going to split it as shown. He's going to get 98 coins. Pirate 4 is going to get no coins. Pirate 3 is going to get 1 coin. Pirate 2 is going to get none. And Pirate 5 is going to get 1 coin. Both Pirate 3 and Pirate 1 recall that if they do not accept this offer, then they will instead get nothing. So they're forced to accept this rather poor offer. Voting commences, no need for a tiebreak, and the money is delivered as shown. So this is one example of a pretty interesting sequential game. They can get really complex really fast. So I'm going to show you a different game that is incredibly complicated. Uh, I mean, it's a very simple game. It only involves two players, but the proof for what is correct is actually very difficult. So let me pull it up very quickly because I thought this would go longer, but I guess I went a bit faster than I intended. So give me a minute. Okay. Let me zoom. Alrighty, so this is the angel problem. How many of you know who John Conway is? You see one yes. Game of Life, exactly. Okay. So people seem to know who John Conway is from the Game of Life. Yeah. If you don't know what the Game of Life is, I mean, I guess search it up. It's interesting within itself, but that's more of a math problem than a game theoretic problem. So let's quickly read this. This is the paper he wrote. I don't know what, well, 1996, on a problem he defined called the angel problem. So let's just quickly read his abstract. Um, can the devil, who removes one square per move from an infinite chessboard, strand the angel, who can jump up to 1,000 squares per move? It seems unlikely, but the answer is unknown. We don't really care about the rest of the abstract. So that's the general point. So basically, we have this grid, and let's say that the angel, we'll mark the angel with this nice yellow, and the angel can move within a radius of something, right? Not a radius, but within the square. So let's see that the angel can move anywhere within this square. During its turn. And then when it changes to the devil's turn, the devil places some red square here. And then the angel can no longer move to that square. So now the angel will move, and the angel is going to move somewhere in this square. So let's say that they go here. And now the angel can move anywhere in this square. I don't remember what size square we did, but now the angel can move anywhere in this square, except for that red space, because that's been blocked off. So now the question is, who is going to win this game, the angel or the devil, right? So, and now I should probably say that now the devil gets to mark another place on the board where the angel is not allowed to go. So let's say that the devil marks here, for example. So where can the angel, I mean, not where can the angel, who's going to win, right? It's a pretty interesting problem. And the proof for who's going to win is incredibly hard to read. It is a really tough problem. And this is another example of a problem that I would advise against doing a game tree for, because the tree is going to be huge. In fact, the devil has infinite places he can place his square given a turn, so you can't even make a tree. So who's going to win? I'm just curious what people think. The angel wins simply by the angel. The devil wins if it traps the angel, and the angel wins if you can prove that the angel can survive infinitely. Okay, people are saying the angel, which is interesting. But let's consider something. Instead of looking at what happens, I guess, let's look at some very specific cases. That's how John Conway writes his paper, and that's how I'm going to write this paper. Not paper, but describe the question. So, first of all, let's consider one thing that's kind of important. So, I don't know if there's hotkeys here or something. So, given an angel that can move within a specific distance, I really screwed up that square. Let's pretend that this is a square. I don't care. Where should this angel move during a given turn? Now, the answer is actually kind of obvious. The angel should always move to one of the edges. Okay, that's an important point. The box is infinite. Where Okay, so because if you only have limited spaces to move, the devil can slowly make a border X blocks wide and slowly close in on the angel. The thing is, though, that's not exactly true, though, because if the angel moves fast enough, it can simply move away from any boxes, right? If it sees that you're making a line, it can just move in that direction. Yeah, the angel can just move in one direction continuously. That's actually not true. If you know that the angel is going to move in one direction constantly, then the devil, given the speed of the angel, can decide to create a kind of horseshoe around where it knows it's going to be. And then when the angel kind of slips into its trap, it shuts the door before the angel can leave, right? So, so now people are saying the devil, which is good. I like discussion. That's probably the best thing that can come out of this class. So it is, it's allowed to jump over points. Wait, is it? Let me read the question. Okay, so here's the paper. So let's read what he has to say. So the angel and devil play their game on an infinite chessboard with one square for each ordered pair of integers x, y. On his turn, the devil may eat any square of the board whatsoever. The square is no longer available to the angel. The angel is a chess piece that can move to any uneaten square that is at most 1,000 king's moves away from the present position. So it can move within a certain radius, pretty much. The angel has wings, so it does not matter if any intervening squares have already been eaten. So it is allowed to jump. It's allowed to border jump. There's your answer. I was pretty sure of that. I just wanted to make sure. So, in essence, if the angel is only going by one, then the devil could hypothetically make a box such that if it is of radius 2, not radius 2, but if it's of thickness 2, then the angel is trapped. That's what the devil has to do. The devil has to make a border thick enough such that the angel is trapped. Now, due to the discussion, I want to point out that the answer is, in fact, the angel. The angel can win. But John Conway demonstrates that certain players, like playing strategies, will end up in the devil winning. For example, if the angel is just going to go straight in one direction, and by that I mean it always increases or decreases as x and or y component, then the angel devil will win, which is an interesting observation. Another interesting observation is that the angel should never go into a square that isn't on the very border of where it's allowed to go, right? So the reason for that is basically, I mean, it's pretty simple actually. The angel basically wastes a turn, right? That allows the devil to add an extra point that wouldn't have been there if the angel had gone farther. So the angel should always go as far as possible. And it should never go back on previous points to points it has previously gone onto, because doing that circle just gives the devil more time. So interestingly enough, the angel is actually deleting more points than the devil is in a way. So let's just continue reading the paper. This introductory paper isn't actually that complex. So he just talks about some strategies here. So basically, if you create an angel that, I don't know the exact algorithm that the angel has to use to win, but if you use an angel that's pretty simple, the devil will win. If it only goes in one direction, if it continues in a spiral, the devil will create a large enough box around where the angel will be in order to win. If you create an angel that is susceptible to certain devil patterns, I guess, like if the angel notices that suddenly the devil is building a horseshoe on one side, then the devil can suddenly trick the angel into avoiding a certain sized horseshoe while falling into a larger horseshoe. So I don't know where the actual proof is. It was made by some guy. It's about 100 pages, I think. Uh, it's not light reading. So I can send you guys the original Conway document, and I'll also search for the proof. I don't know who wrote it. I know it exists, and I could send you guys that. Would you like that, or I mean, I'll put it regardless if you like it. So yeah, um, yeah. So I guess that's all I really have to say today. So we're ending like 5 minutes early. So are there any concluding questions? I don't see any questions. Oh, I like this more than my geometry class. That's good. Um, I had a terrible geometry teacher. I don't know if you do, but she was terrible. Yeah, I'm going to assume that there aren't any questions. So I'm going to stop share. We're going to end like 5 minutes early. If you have any questions, say them now because I'm stopping. 3, 2, 1. Okay, no more questions. If you have a question, save it for next time. It's been great teaching you. I'll see you everybody next week, next Tuesday, same time, same whatever. So I hope everybody had a good class, and I'll see you next week. Bye-bye.
Bye.